Right now, somewhere in our galaxy, there is a dead star sitting on the edge of oblivion. It is not a black hole, not yet. But it is so close to becoming one that the matter inside it has been crushed into something that no longer resembles anything you have ever seen or touched. The atoms are gone. The neutrons themselves may be breaking apart. And gravity, the most patient force in the universe, is pressing inward with such relentless power that only the strangest, most extreme states of matter still stand in its way. This is what happens in the space between survival and total collapse, a place where the laws of physics are pushed to their absolute breaking point. And tonight, we are going inside that star to witness what matter becomes when it is one step away from disappearing from the universe forever. Before we go any further, if you find this kind of deep exploration fascinating, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. To understand what happens inside a star that almost becomes a black hole, you first need to understand how a star reaches that point. And it begins, perhaps surprisingly, with one of the most violent events in the entire universe: the death of a massive star. Not all stars die the same way. The Sun will burn for about 10 billion years and leave behind a white dwarf, a quiet death. But stars with masses 8, 10, 20, even 50 or more times the mass of the Sun burn through their fuel at a furious pace. A star 50 times the mass of the Sun might exhaust its fuel in just a few million years. These massive stars live fast and die violently. And it is inside the corpses of these massive stars that we find the most extreme conditions matter can endure. Here is the key to understanding what happens. A star is fundamentally a battle, a war between two forces that has been raging since the star was born. On one side is gravity, the force that wants to crush the star inward, to collapse all that mass into the smallest possible space. On the other side is the energy generated by nuclear fusion in the core, pushing outward, resisting gravity's pull. For most of a star's life, these two forces are in balance. Gravity pulls inward, fusion pushes outward. The star holds its shape. It shines steadily across the darkness. But fusion is not infinite. The fuel runs out. And when it does, gravity wins. In a massive star, fusion proceeds through a series of stages, each one producing heavier elements, and each one lasting a shorter amount of time than the one before it. The first stage is hydrogen fusion, the same process that powers our Sun. Hydrogen nuclei, which are simply individual protons, are fused together under tremendous heat and pressure to form helium. This is the longest stage. In a star 20 times the mass of the Sun, hydrogen fusion in the core might last about 10 million years. That sounds like a long time, and it is by human standards. But by stellar standards, it is already burning fast. The Sun will burn hydrogen for 10 billion years. A star 20 times more massive gets through the same stage in a fraction of that time, because the temperatures and pressures in its core are so much greater. When the hydrogen in the core is exhausted, the core contracts under gravity. This contraction raises the temperature and pressure even further, until conditions become extreme enough to ignite the next fuel: helium. Helium nuclei fuse together to form carbon and oxygen. This stage is shorter. In that same 20 solar mass star, helium burning might last about 1 million years. Already the pace is accelerating dramatically. When the helium is gone, the core contracts again and carbon ignites. Then neon, then oxygen, then silicon. Each stage is dramatically shorter than the last. Carbon burning lasts perhaps 1,000 years. neon about a year, oxygen maybe 6 months, and silicon, the final stage, lasts about a single day. In the most massive stars, it can be over in hours. The star races through its fuel at an ever-increasing pace, building up heavier elements in layer upon layer, like the rings of an onion. And at the very center, a ball of iron. And here is where everything changes. Because iron is different from every element that came before it. Iron is the end of the line. Every stage of fusion up to this point has released energy. When hydrogen fuses into helium, energy is released. When helium fuses into carbon, energy is released. When carbon fuses into neon, when neon contributes to oxygen, when oxygen fuses into silicon, energy is released at every step. That released energy is what generates the outward pressure that holds the star up against gravity. Fusion is the engine that keeps the star alive. But iron is the most tightly bound nucleus in nature. Its protons and neutrons are held together so efficiently that fusing iron into heavier elements does not release energy. It consumes energy. It actually takes energy away from the core rather than adding to it. Fusing iron is like trying to squeeze water from a stone. There is nothing left to extract. This means that once the core of a massive star is made of iron, fusion can no longer save it. The engine stops. The outward pressure that has been holding the star up for millions of years simply vanishes. And gravity, which has been waiting patiently all this time, pressing inward with relentless force, suddenly finds that nothing is pushing back. What happens next takes less than a single second. The iron core at this point is roughly the size of Earth, but contains about 1.5 solar masses, supported by electron degeneracy pressure. But material keeps raining down from above, adding mass. When the core exceeds approximately 1.4 solar masses, the Chandrasekhar limit, electron degeneracy pressure, fails completely, and the core collapses. The collapse is almost instantaneous. The core falls inward at speeds reaching 1/4 of the speed of light. In less than a second, a region the size of Earth is crushed down to a sphere roughly 20 kilometers across. That is about the distance you might drive across a small city. All the mass that was spread across thousands of kilometers is suddenly compressed into a ball smaller than most islands. The gravitational energy released during this collapse is staggering. More energy pours out in that fraction of a second than the Sun will produce in its entire 10 billion year lifetime. During this collapse, something extraordinary happens at the atomic level. The electrons that were providing the degeneracy pressure are forced into the protons in the iron nuclei. Electrons and protons merge together to become neutrons, releasing a flood of ghostly particles called neutrinos. This process is called neutronization. In a fraction of a second, the collapsing core transforms from a mixture of iron nuclei and electrons into a sea of almost pure neutrons. An object made almost entirely of neutrons, packed together so tightly that they are essentially touching. An object so dense that a single teaspoon of its material would weigh roughly 4 billion tons on Earth. More than every ship sailing in every ocean on the planet. More than every building in a major city combined. A single teaspoon. This is a neutron star. And the moment of its birth is accompanied by one of the most powerful explosions in the universe. When the collapsing core reaches neutron star densities, it suddenly stiffens. The collapse halts. The infalling material bounces outward. This bounce, combined with the neutrino flood, drives a shock wave through the rest of the star, the supernova explosion. The outer layers are blasted into space at tens of thousands of kilometers per second, scattering elements that will form new stars and planets. Nearly every heavy element on Earth was forged inside a massive star and scattered by a supernova. But the outer layers are not what interests us tonight. What interests us is what stays behind. The remnant. The core. The neutron star sitting at the center of the expanding debris cloud, glowing with unimaginable heat, spinning rapidly, pulsing with energy. Because here is the crucial question: how massive is that remnant, and how close is it to the edge? Not all neutron stars are the same. Some are relatively lightweight, perhaps 1.2 or 1.3 times the mass of the Sun. These neutron stars are incredibly dense and extreme by any normal standard, but they are comfortably supported by the internal pressures that resist gravitational collapse. They will exist as neutron stars effectively forever, slowly cooling over trillions of years, quietly spinning in the darkness of space. They are stable. They are safe. But some neutron stars are much more massive. Some are born with masses closer to 2 times the mass of the Sun, and some, through interactions with companion stars or through mergers with other neutron stars, can gain even more mass over time, pushing them toward a critical limit. This limit is called the Tolman-Oppenheimer-Volkoff limit, named after the physicists who first calculated it in 1939. It is the maximum possible mass that a neutron star can have before gravity overwhelms all internal pressure and the star collapses into a black hole. The exact value of this limit is one of the biggest open questions in astrophysics. We know it is somewhere around 2 to 2.5 times the mass of the Sun, but the precise number depends on the behavior of matter at densities so extreme that we cannot reproduce them in any laboratory on Earth. The densities inside a neutron star near this mass limit are several times higher than the density of an atomic nucleus. We are talking about conditions where each cubic centimeter of material weighs hundreds of millions of tons, where matter is compressed to a state that has never existed on Earth, not even in the most powerful particle accelerators humans have ever built. And here is what makes this so fascinating. We know the limit exists. We know that below it, neutron stars can survive, held up by internal pressures that resist gravity's pull. And we know that above it, nothing can prevent collapse. The star falls through its own event horizon and becomes a black hole. But right at the boundary, right at the threshold, something extraordinary is happening to the matter inside. To appreciate what is happening at the threshold, you need to understand just how extreme the conditions have become. We are no longer talking about ordinary matter in any sense. Ordinary matter, the stuff you interact with every day, is made of atoms. Atoms are mostly empty space, a tiny nucleus at the center made of protons and neutrons, surrounded by a vast cloud of electrons at relatively enormous distances. If an atom were the size of a football stadium, the nucleus would be a marble sitting at the center of the field. Everything else is empty. In a neutron star, all of that empty space has been crushed out of existence. The electrons have been forced into the protons. The atoms themselves no longer exist. There are no electron clouds. There are no individual nuclei sitting in a sea of electrons. Everything has been compressed down to nuclear densities. Neutrons packed together so closely that they are essentially touching. The entire star is like one enormous atomic nucleus, roughly 20 kilometers across, containing more mass than the Sun. The average density of a neutron star is about 400 trillion grams per cubic centimeter. For comparison, water is 1 gram per cubic centimeter. The core of the Earth is about 13. A white dwarf reaches about 1 million. A neutron star is 400 trillion. That number is so far beyond ordinary experience that the density itself becomes difficult to process as a meaningful quantity. And for neutron stars near the Tolman-Oppenheimer-Volkoff limit, the densities in the deep core are even higher than this average. The core density of a near-threshold neutron star may reach several times the density of an ordinary atomic nucleus, or even higher. These are densities that exceed anything we have ever created or observed directly in a controlled setting. They are densities where the fundamental behavior of matter becomes genuinely uncertain, where our best theories of nuclear physics are being pushed beyond the regimes in which they have been tested and verified. This is the regime we are going to explore, the near-threshold regime, the interior of a star that is almost, but not quite, a black hole. What makes this regime so extraordinary is that gravity is nearly winning. In a lower mass neutron star, gravity is strong, incredibly strong, far stronger than anywhere else in the universe outside of a black hole. The surface gravity of a neutron star is roughly 200 billion times stronger than Earth's surface gravity. If you could somehow stand on a neutron star, which you obviously cannot because you would be crushed into a thin film of matter and then disintegrated entirely, but if you somehow could, you would weigh roughly 20 trillion pounds. Light itself is noticeably bent by the gravitational field. If you looked outward from a neutron star's surface, the curvature of space-time would allow you to see more than half of the star's surface at once, because light from the far side bends around toward your eyes. Neutron stars are objects where general relativity, Einstein's theory of gravity, is not a subtle correction to Newtonian physics. It is the dominant framework. Gravity here is so strong that it warps space and time in ways that would be immediately visible and tangible if you could somehow witness them. But even with all of this, in a typical neutron star, the internal pressures still win. Gravity pulls inward with enormous force, but the pressure from the compressed neutrons pushes back harder. There is a margin. The star is dense and extreme, but it is stable. It will persist. In a near-threshold neutron star, that margin is vanishingly thin. Gravity is pulling inward with nearly the same force that the internal pressure can muster. The star is barely holding on. It is balanced on a knife edge, with the abyss of total gravitational collapse on one side and continued survival on the other. And inside this star, the matter is being subjected to conditions so extreme that it may be transforming into states that have never been directly observed and that physicists cannot fully predict. The physics that governs what happens inside this near-threshold star involves some of the most fundamental questions in all of science. What is matter made of at the deepest level? How does it behave under the most extreme conditions the universe can produce? And where is the absolute limit, the point at which no form of matter, no pressure, no force can resist gravity any longer? These are not abstract questions. They have real answers. There are real neutron stars in our galaxy right now, sitting at or near the Tolman-Oppenheimer-Volkoff limit, containing matter in states we cannot replicate on Earth. And the answers to these questions have implications far beyond astrophysics. They connect to fundamental nuclear physics, to the behavior of the strong force that holds atomic nuclei together, to the nature of matter at densities where individual particles may lose their identity entirely. To understand what the matter inside these stars might be doing, you first need to appreciate something about how nuclear physics works at extreme densities. Under normal conditions, the strong nuclear force holds protons and neutrons together inside atomic nuclei. This force is enormously powerful at short ranges. It is what keeps the nucleus from flying apart despite the electrical repulsion between all those positively charged protons packed so closely together. At the distances found inside an ordinary nucleus, the strong force is attractive. It pulls nucleons together, binding them into stable configurations. But the strong force has a peculiar property. At very short distances, shorter than the normal spacing between nucleons in a nucleus, the strong force becomes repulsive. It pushes nucleons apart rather than pulling them together. This is sometimes called the hard-core repulsion of the nuclear force. Under normal conditions, this repulsive behavior does not matter because nucleons never get close enough for it to activate. The attractive part of the force holds them at a comfortable distance, and the repulsive core remains dormant. But inside a neutron star near the mass limit, matter is compressed to such extraordinary densities that neutrons are being pushed far closer together than they would ever be in an ordinary atomic nucleus. The spacing between neutrons shrinks to the point where this short-range repulsion becomes critically important. It is one of the key sources of pressure that resists gravitational collapse at the highest densities. Without this repulsion, neutron stars could not exist at the masses we observe them. They would collapse into black holes at much lower masses than the Tolman-Oppenheimer-Volkoff limit allows. But here is the deep challenge. We do not fully understand how the strong force behaves at the extreme densities found in the cores of the most massive neutron stars. Our best theory of the strong force, quantum chromodynamics, is extraordinarily successful at describing particle interactions at high energies in accelerators. But calculating the behavior of dense nuclear matter from first principles using quantum chromodynamics is one of the hardest problems in all of theoretical physics. The mathematics is so complex that even the most powerful supercomputers in the world can only handle simplified approximations. And the densities in the core of a near-threshold neutron star exceed anything we can probe directly in any laboratory by a significant margin. This means there is genuine uncertainty about what matter is doing in the deepest cores of these stars. We have theories, we have models, we have educated guesses based on extrapolating from conditions we can study in laboratories and particle accelerators. But we do not have definitive answers. And the answers matter enormously because the behavior of matter at these densities determines the maximum mass a neutron star can support. It determines whether a particular collapsing star becomes a neutron star or a black hole. It determines the precise location of the threshold between survival and oblivion. The relationship between pressure and density inside a neutron star is described by something physicists call the equation of state. The equation of state tells you how much pressure matter produces at a given density. If the equation of state is stiff, meaning matter produces a lot of pressure even at extreme densities, then neutron stars can support higher maximum masses. The Tolman-Oppenheimer-Volkoff limit is higher. More massive remnants can survive as neutron stars rather than collapsing into black holes. If the equation of state is soft, meaning matter produces less pressure at extreme densities, then neutron stars cannot support as much mass. The maximum mass is lower. Remnants that would have survived with a stiff equation of state will instead collapse into black holes. Determining the true equation of state of ultra-dense matter is one of the great goals of modern astrophysics and nuclear physics. It connects the largest scales of the universe, the deaths of massive stars, the collisions of neutron stars, the formation of black holes, to the smallest scales imaginable. The behavior of quarks and gluons, the fundamental particles that make up protons and neutrons, under conditions of unimaginable density and pressure. And we are making progress. Gravitational wave observations of neutron star mergers, precise pulsar mass measurements, and X-ray observations from the NICA instrument aboard the International Space Station are all converging on constraints for the equation of state. These observations have ruled out both the stiffest and the softest theoretical proposals and are narrowing the possibilities. But within these constraints, there is still enormous room for different physical scenarios in the deep interior. These observations are converging on a picture. The equation of state appears to be moderately stiff. Neutron stars can support masses up to at least 2 times the mass of the Sun, possibly somewhat higher. Their radii are roughly 10 to 13 kilometers, and the densities in their cores reach several times the density of an ordinary atomic nucleus. But within these constraints, there is still enormous room for different physical scenarios in the deep interior. The matter in the core could be made of neutrons interacting through the strong nuclear force in ways we have not yet fully characterized. It could contain exotic particles never observed in any laboratory on Earth. It could exist in a state where the neutrons themselves have dissolved into their constituent quarks, forming a plasma of deconfined quark matter. All of these possibilities are consistent with current observations, and distinguishing between them is one of the great challenges facing physics today. What we do know is this. As you go deeper into a neutron star near the mass limit, conditions become more and more extreme. The density climbs, the pressure mounts, gravity pulls harder, and the matter is forced into configurations that push the very limits of what physics allows before total collapse. At some point, somewhere inside these stars, matter reaches a state that exists nowhere else in the observable universe. A state that sits on the boundary between the survival of physical substance and the formation of a region of pure space-time curvature from which nothing can ever return. The concept of a threshold is itself remarkable when you think about it carefully. In most areas of physics, changes happen gradually. Water gets warmer degree by degree until it boils. Pressure builds slowly until a material fractures. But the threshold of black hole formation is different. It is absolute. Below the threshold, matter exists. It has structure, it has properties, it has pressure and temperature and density. It resists gravity. It occupies space. It is something. Above the threshold, none of that matters. Gravity wins completely. The matter collapses behind an event horizon. The structure is gone. The properties are gone. What was once a physical object, made of particles interacting through forces, becomes a region of space-time defined entirely by its mass, its spin, and its electric charge. Nothing else survives. No information about what the matter was made of, no record of its composition or temperature or internal structure. All of that is hidden behind the event horizon, cut off from the rest of the universe forever. And so, the near-threshold regime, the interior of a star that almost becomes a black hole, is the last place where matter gets to be matter. It is the final stand, the last frontier of physical structure before gravity wipes the slate clean. And what matter does in that final stand, how it resists, what forms it takes, what pressures it can generate, tells us everything about the ultimate limits of the physical world. That is why this regime matters so deeply, not just as an astrophysical curiosity, not just as one detail in the story of stellar evolution, but as a fundamental statement about the nature of reality itself, about what the universe allows to exist and what it does not, about the boundary between substance and void, between matter and geometry, between a star that is something and the black hole that, in a certain profound sense, is nothing but curved, empty space. And to understand what happens at that boundary, we need to descend into the interior. We need to go layer by layer through the structure of a near-threshold neutron star and examine what matter actually becomes when gravity has almost won. Because what we find there will challenge everything you think you know about what matter is, what it can endure, and what it ultimately becomes when the universe pushes it to the very edge of existence. Now we descend. We are going to travel into the interior of a neutron star that sits right at the edge of the maximum mass it can possibly sustain. A star so dense that the matter inside it has been transformed beyond anything you would recognize, beyond anything that exists anywhere else in the known universe. And what we find as we go deeper will reveal one of the most profound mysteries in modern physics. Because the truth is, nobody knows for certain what the deepest interior of this star is made of. We have theories, we have models, we have brilliant physicists spending entire careers trying to answer this question, but the answer remains elusive. And the reason it remains elusive is that the conditions inside this star are so extreme that they push our understanding of matter itself to the breaking point. Let us start at the surface and work our way down, because the transformation that matter undergoes inside a near-threshold neutron star does not happen all at once. It happens in stages, layer by layer. As the density climbs and the pressure mounts, matter changes its character in ways that become progressively more alien and more extreme. The journey from surface to core is a journey through the entire range of what matter can be, from something vaguely recognizable at the top to something utterly unknown at the bottom. The outermost layer, the outer crust, is surprisingly familiar. Atomic nuclei, primarily iron, arranged in a crystal lattice with free electrons between them. The nuclei are the same kind found in ordinary matter. The difference is the density, already roughly 1,000,000 grams per cubic centimeter, even at the surface. That is about the density of a white dwarf star. A teaspoon of material from the outer crust of a neutron star would weigh several tons on Earth. But the fundamental structure, nuclei in a lattice with electrons, is still recognizable. You could still point at it and say, that is matter. That is atoms, or at least atomic nuclei, arranged in a pattern. But as you go deeper, the pressure increases and the density climbs, and the nuclei begin to change. Under the crushing weight of the material above, the nuclei in the crust are squeezed together more and more tightly, and something happens that does not occur under any conditions on Earth. The nuclei become increasingly neutron-rich. Under normal conditions, atomic nuclei contain a roughly balanced mixture of protons and neutrons. Iron, for example, has 26 protons and typically 30 neutrons. This balance is maintained by the interplay between the strong nuclear force, which binds the nucleus together, and the electromagnetic repulsion between protons, which tries to push the nucleus apart. But in the crust of a neutron star, the pressure is so extreme that it becomes energetically favorable for electrons to be captured by protons, converting them into neutrons. This is the same process that occurred during the initial collapse that created the neutron star. But now it is happening gradually as you descend through the crust. The nuclei become more and more neutron-heavy. Instead of iron with its familiar balance of protons and neutrons, you start finding nuclei with 50, 60, 70, 80 or more neutrons packed into each nucleus, with only a modest number of protons remaining. These are nuclei that do not exist in nature under any ordinary circumstances. They are too neutron-rich to be stable in a laboratory. On Earth, they would fly apart in a fraction of a second, shedding their excess neutrons through radioactive decay. But here, in the crushing environment of a neutron star crust, the immense pressure prevents them from decaying. They are held together by brute force, stabilized by the weight of everything above them pressing down. As you descend further into what physicists call the inner crust, you reach a critical transition point called the neutron drip line. At this depth, the nuclei have become so bloated with neutrons that they simply cannot hold any more. Neutrons begin to leak out of the nuclei, dripping free into the surrounding space. Below the neutron drip line, you have a bizarre two-phase material. There are still nuclei, enormously neutron-rich nuclei, sitting in a lattice. But now those nuclei are immersed in a gas of free neutrons. Neutrons that do not belong to any nucleus. Neutrons that have been squeezed out of the nuclei by the immense pressure and now flow freely between them like a fluid filling the gaps in a sponge. This is already profoundly strange. On Earth, free neutrons decay in about 10 minutes. But inside a neutron star, the Pauli exclusion principle blocks the decay products from occupying any available quantum state. The neutrons are forced to remain neutrons, trapped by the quantum mechanical properties of the matter around them. And here, in the inner crust, something truly remarkable happens to the shapes that matter takes. As the density continues to rise, and you approach the transition from the crust to the core, the competition between the strong nuclear force holding nuclei together and the gravitational and electromagnetic forces squeezing them produces structures that physicists have given a wonderfully evocative name: nuclear pasta. Nuclear pasta. It sounds like something from a kitchen, and that is exactly why physicists chose the name. Because the shapes that matter in this transition region look eerily similar to different types of Italian pasta. At lower densities, nuclear matter forms roughly spherical blobs, the gnocchi phase. As density increases, these elongate into cylindrical rods, the spaghetti phase. Denser still, rods merge into flat sheets, the lasagna phase. Then the geometry inverts. Cylindrical tubes of neutron fluid run through nuclear material, anti-spaghetti. Finally, spherical bubbles of neutron fluid sit within nuclear material, the Swiss cheese phase. Each transition reflects the changing balance between nuclear surface tension, electromagnetic repulsion, and gravitational pressure. These are not whimsical speculations. Nuclear pasta phases are the result of detailed calculations by nuclear physicists using sophisticated models of how nuclear matter behaves under extreme pressure. The calculations show that in the narrow density range of the transition between the crust and the core, these unusual geometries represent the lowest energy configurations of the matter. Nature prefers the arrangement that minimizes energy, and at these particular densities, spaghetti and lasagna and their cousins represent the most energetically favorable shapes. The matter is not choosing to look like pasta. The fundamental physics of the strong nuclear force and the competition between surface tension and Coulomb repulsion and gravitational pressure force it into these configurations. A nuclear pasta may be one of the strongest materials in the universe. Calculations suggest that the breaking strain of nuclear pasta, the amount of force required to deform or shatter it, exceeds that of any known material by an enormous margin. It may be 10 billion times stronger than steel. The crust of a neutron star, where these pasta phases exist, may be the most rigid, most durable solid structure in the cosmos. And it exists only in the bizarre transition zone between the ordered crystal lattice of the outer crust and the fluid interior of the core. Now we pass through the pasta layers and enter the core, and this is where everything changes completely. In the outer core, just below the crust, the last remnants of nuclear structure vanish. There are no more nuclei, no more lattice, no more pasta shapes. The density has risen to the point where individual nuclei have merged together into a continuous fluid of nuclear matter. You are now in a sea of neutrons, with a small admixture of protons and electrons, about 95% neutrons, about 5% protons and electrons. This is nuclear matter in bulk, not organized into separate nuclei, but flowing freely as a fluid. And this fluid has extraordinary properties. At the densities found in the outer core, the neutrons may form what is called a superfluid. A superfluid is a quantum state of matter in which a fluid flows with zero viscosity, no friction, no resistance to flow. Once set in motion, a superfluid will continue flowing forever without slowing down. Superfluidity is a quantum mechanical phenomenon that occurs when particles form pairs, and those pairs behave collectively as a single quantum state. On Earth, superfluidity has been observed in liquid helium cooled to temperatures near absolute zero. In a neutron star, the neutrons in the outer core are believed to form pairs called Cooper pairs, and these paired neutrons create a superfluid state. This neutron superfluidity has observable consequences. The most dramatic are pulsar glitches. A neutron star that has been spinning at an extraordinarily stable rate, ticking like one of the most precise clocks in the universe, abruptly speeds up. The change is tiny in absolute terms, a fractional increase in rotation rate. But for an object this massive, spinning this fast, the energy involved is enormous. What appears to be happening is that the superfluid neutrons in the interior, which can rotate independently of the solid crust, develop a lag. The crust slows down gradually due to magnetic braking, but the superfluid, flowing without friction, maintains its original rotation rate. The difference builds over time until it reaches a critical threshold, at which point angular momentum is suddenly transferred from the superfluid to the crust. The crust lurches forward, the pulsar speeds up. Then the process begins again, the crust gradually slowing, while the superfluid maintains its frictionless spin, building toward the next glitch. Some pulsars glitch regularly every few years. Others glitch rarely and unpredictably. The pattern depends on the internal structure, on how much superfluid exists, and how it couples to the crust. Every glitch is a message from the interior, a brief window into conditions we cannot observe directly. A pulsar glitch is sudden and dramatic. A neutron star that has been spinning at an extraordinarily stable rate, ticking like the most precise clock in the universe, abruptly speeds up. The change is tiny in absolute terms, a fractional increase in rotation rate. But for an object this massive, spinning this fast, the energy involved is enormous. What appears to be happening is that the superfluid neutrons in the interior, which can rotate independently of the solid crust, develop a lag. The crust slows down gradually due to magnetic braking, but the superfluid, flowing without friction, maintains its original rotation rate. The difference builds over time until it reaches a critical threshold, at which point angular momentum is suddenly transferred from the superfluid to the crust. The crust lurches forward, the pulsar speeds up. Then the process begins again, the crust gradually slowing, while the superfluid maintains its frictionless spin, building toward the next glitch. Some pulsars glitch regularly every few years. Others glitch rarely and unpredictably. The pattern depends on the internal structure, on how much superfluid exists, and how it couples to the crust. Every glitch is a message from the interior, a brief window into conditions we cannot observe directly. The protons in the outer core may similarly form pairs and become superconducting, the charged particle equivalent of superfluidity. A superconductor carries electric current without resistance. Superconducting protons in the core would affect the neutron star's magnetic field, potentially explaining some of the extraordinary magnetic phenomena observed in magnetars, neutron stars with magnetic fields trillions of times stronger than Earth's. But we are not yet at the regime that truly interests us tonight. The outer core, with its superfluid neutrons and superconducting protons, is extreme by any normal standard. But it is not the edge. It is not the threshold. To reach the threshold, you must go deeper still, into the inner core, where densities climb to several times the density of a normal atomic nucleus. And here, in the innermost heart of a near-threshold neutron star, is where the greatest mystery lies. Because at these densities, neutrons may not remain neutrons. To understand what might happen, you need to know a little bit about what neutrons are made of. A neutron is not a fundamental particle. It is made of 3 quarks, specifically 2 down quarks and 1 up quark, bound together by the strong nuclear force, which is carried by particles called gluons. In ordinary matter, quarks are always confined inside protons and neutrons. You never see a quark by itself. This confinement is one of the most distinctive properties of the strong force. If you try to pull 2 quarks apart, the force between them does not decrease with distance like gravity or electromagnetism. Instead, it stays constant or even increases. The energy required to separate two quarks grows so quickly that before they can come apart, the energy creates new quark pairs from the vacuum. You end up with new particles rather than free quarks. This is why isolated quarks have never been observed. But here is the crucial point. At extremely high densities, the kind of densities found in the deep cores of near-threshold neutron stars, something extraordinary may happen. When neutrons are squeezed so close together that the quarks inside neighboring neutrons are practically on top of each other, the boundaries between individual neutrons may dissolve. The quarks that were confined inside their respective neutrons may become liberated, free to roam across the entire core rather than being locked inside individual particles. The neutrons literally melt into their constituent parts. This state of matter is called deconfined quark matter, or sometimes quark-gluon plasma, when it occurs at high temperatures. If it exists inside neutron stars, it would represent a fundamentally different phase of matter. Not neutrons, not protons, not any recognizable particle. Just quarks and gluons, the most elementary building blocks of nuclear matter, swimming in a dense soup without any individual identity. Every quark belonging to no particular neutron, every gluon carrying force between quarks that are no longer organized into discrete particles. This is one of the most tantalizing possibilities in all of astrophysics. If the cores of the most massive neutron stars contain deconfined quark matter, then these objects contain a phase of matter that has never been stably produced in any laboratory. Particle accelerators like the Large Hadron Collider have created tiny droplets of quark-gluon plasma by smashing heavy nuclei together at nearly the speed of light. But these droplets are incredibly brief, lasting for only a few trillionths of a second before the quarks reconfine into ordinary particles. Inside a neutron star, quark matter could be stable. It could persist for billions of years, held in place by the immense gravitational pressure of the star above it. A permanent state of deconfined matter, existing in the most extreme environment the universe has to offer. The presence of quark matter in the core would fundamentally alter the properties of the star. It would change the relationship between pressure and density, the equation of state, in ways that affect the maximum mass a neutron star can sustain, its radius, and how it responds to perturbations like tidal forces during a merger. Some models predict that the transition from neutron matter to quark matter is smooth, a gradual crossover where neutrons slowly dissolve as density increases. Other models predict a sharp first-order phase transition, a sudden jump from neutron matter to quark matter at a specific density, similar to how water suddenly changes from liquid to gas at its boiling point. If the transition is sharp, it could produce observable signatures. A neutron star with a quark matter core might have a slightly different mass-radius relationship than one without, and this difference might be detectable by instruments like those aboard current and future X-ray observatories. But quark matter is not the only exotic possibility. There are other particles that might appear in the deep cores of near-threshold neutron stars. Particles that are heavier than neutrons, but that become energetically favorable to produce under extreme conditions. These are called hyperons. Hyperons are baryons, particles made of three quarks, just like protons and neutrons. But while protons and neutrons are made exclusively of up quarks and down quarks, hyperons contain one or more strange quarks. The strange quark is heavier than the up and down quarks, which means hyperons are heavier than protons and neutrons. Under normal conditions, hyperons are unstable. They decay in a tiny fraction of a second into lighter particles. You can produce them in particle accelerators, but they vanish almost immediately. The lambda hyperon, for example, contains one up quark, one down quark, and one strange quark. It has a mass about 19% greater than a neutron. Under normal circumstances, producing a lambda requires significant energy, and the particle decays almost instantly. But in the core of a massive neutron star, the situation is entirely different. Here is why. As the density increases in the core of a neutron star, the neutrons become more and more energetic. The Pauli exclusion principle forces each neutron into a progressively higher energy state because all the lower energy states are already occupied. At some critical density, the energy of the most energetic neutrons exceeds the rest mass energy of a lambda hyperon. At that point, it becomes energetically cheaper for the system to convert a high-energy neutron into a lower-energy lambda hyperon plus other particles, rather than continuing to stack neutrons into ever higher energy states. The system lowers its total energy by producing hyperons. This is a remarkable idea. The star reduces its energy, and therefore its pressure, by creating heavier, more exotic particles. Lambda hyperons appear first because they are the lightest hyperons. But as density continues to increase, even heavier hyperons might appear. The sigma hyperon, which also contains a strange quark, but in a different configuration, could emerge. The Xi hyperon, containing two strange quarks, might appear at even higher densities. But there is a problem. A serious problem that has troubled nuclear physicists for decades. If hyperons appear in the core, they reduce the pressure. Remember, the hyperons appear because they lower the energy of the system. But lower energy means lower pressure. And lower pressure means the star is less able to resist gravitational collapse. If hyperons appear in abundance, they soften the equation of state so much that the maximum mass a neutron star can sustain drops well below 2 solar masses. But we have observed neutron stars with masses of about 2 solar masses. They exist, they are real, and they are clearly not collapsing into black holes. This contradiction is called the hyperon puzzle. The physics says hyperons should appear at the densities found in massive neutron star cores, but if they do appear, the star should not be able to support the masses we observe. Something must be preventing the hyperons from softening the equation of state too much. Perhaps additional repulsive forces between hyperons stiffen the matter back up. Perhaps the transition to quark matter happens before hyperons can appear in large numbers, preempting the softening. Perhaps our understanding of hyperon interactions at these densities is simply incomplete. The hyperon puzzle remains one of the most important unsolved problems in nuclear astrophysics, and solving it would tell us an enormous amount about the true nature of matter at the highest densities. There are still other exotic possibilities. At sufficiently high densities, mesons might form what is called a condensate. Mesons are particles made of one quark and one antiquark. The pion is the lightest meson, and it plays a crucial role in carrying the strong nuclear force between nucleons. Under normal conditions, pions are produced and absorbed constantly inside nuclear matter, mediating the force between neutrons and protons. But at extreme densities, the conditions might favor the spontaneous production of vast numbers of pions or kaons, another type of meson containing a strange quark. These particles would not exist as individual particles flying around. Instead, they would form a collective quantum state called a Bose-Einstein condensate, in which enormous numbers of mesons all occupy the same quantum state, behaving as a single coherent quantum entity. A pion condensate, or a kaon condensate, would dramatically alter the properties of the matter in the core. Like hyperons, meson condensates tend to soften the equation of state, reducing the pressure and lowering the maximum mass the star can support. The question of whether these condensates actually form and how they interact with the other components of the matter remains open. It depends on details of meson interactions at extreme densities that are not fully understood. So here is where we stand. We have descended through the outer crust with its crystal lattice of nuclei. through the inner crust with its increasingly neutron-rich nuclei, dripping free neutrons and forming bizarre pasta shapes, through the outer core with its superfluid neutron sea. And now we are in the inner core of a near-threshold neutron star, at densities several times greater than a normal atomic nucleus. And we do not know what the matter here is made of. It could be neutrons, packed incredibly tightly, interacting through the strong nuclear force in ways that are only partially understood. It could be neutrons mixed with hyperons, strange baryons that appear when the density pushes neutron energies above the hyperon production threshold. It could be a condensate of pions or kaons, a collective quantum state of mesons pervading the nuclear fluid. It could be deconfined quark matter, a sea of free quarks and gluons with no individual particle identity. Or it could be some combination of these, with different exotic phases coexisting in different layers of the deep core, separated by phase transitions that we cannot yet predict with confidence. Each of these possibilities represents a different answer to one of the deepest questions in physics. What is matter when you crush it beyond atoms, beyond nuclei, beyond even individual neutrons? The answer is that we are genuinely not sure. The densities exceed anything our accelerators can sustain. We must rely on theory, astronomical observation, and extrapolation. But despite this uncertainty, we know certain things. We know the matter in the deep core is no longer made of anything resembling atoms. The familiar structure of the periodic table, the organized hierarchy of electrons orbiting nuclei, is long gone. It vanished somewhere in the outer crust at densities millions of times lower than what we find here. We know the matter has been compressed beyond the point where individual nuclei can exist. The distinction between one nucleus and another has dissolved into a continuous fluid. We know the density is so extreme that quantum mechanical effects dominate the behavior of the matter at every scale. The Pauli exclusion principle, the uncertainty principle, and the collective quantum behavior of enormous numbers of identical particles are not subtle corrections to classical physics here. They are the primary forces shaping the structure of matter. We know the temperature, while extremely high by human standards, is effectively cold compared to the energy scales involved. A young neutron star might have a core temperature of hundreds of billions of degrees. That sounds incomprehensibly hot. But the Fermi energy of the neutrons, the energy scale set by the Pauli exclusion principle in this dense quantum fluid, is far higher than the thermal energy. The matter is what physicists call degenerate. Its behavior is dominated by quantum statistics rather than thermal motion. In a very real sense, despite being hundreds of billions of degrees hot, the core of a neutron star behaves as though it is cold. The quantum effects are what matter. The temperature is almost irrelevant. And we know that whatever the matter in the core is made of, it is producing enough pressure to prevent gravitational collapse. At least for now. At least for a star below the Tolman-Oppenheimer-Volkoff limit. The matter is resisting gravity through some combination of quantum degeneracy pressure, strong nuclear force repulsion, and possibly other exotic mechanisms we have not yet identified. The pressure is immense. The gravity is immense. And the balance between them is precarious. What we do know is that the matter in this deep core exists at densities that push every branch of physics to its limits simultaneously. Nuclear physics, particle physics, quantum mechanics, and general relativity all converge here, and no single field can handle the conditions alone. The answer to what this matter truly is will come from gravitational wave observations, X-ray measurements, laboratory experiments pushing the boundaries of the strong force, and theoretical breakthroughs connecting quarks and gluons to bulk matter at extreme densities. Whether the deepest interior contains neutrons, hyperons, meson condensates, free quarks, or something we have not yet imagined, remains genuinely open. And finding the answer will tell us something profound about the rules governing what the universe permits to exist at the furthest edge of gravitational survival. We have seen what matter becomes under near-threshold pressure. It transforms from recognizable atomic nuclei through increasingly exotic states until it reaches a form that pushes against the very boundaries of our knowledge. But matter does not simply exist at these densities passively. It fights back against gravity. It resists collapse through forces and pressures that are among the most powerful phenomena in nature. And understanding how that resistance works, what forces are holding the star together, and why those forces have limits, is essential to understanding why a near-threshold neutron star is different from a black hole, why it exists at all, and why, under certain circumstances, even the most powerful resistance the universe can muster is simply not enough. We have traveled deep into the interior of a neutron star, sitting at the edge of gravitational collapse. We have watched matter transform from recognizable atomic nuclei at the surface into something utterly alien at the core. But all of that transformation is not merely a passive response to being squeezed. It is resistance. Every change the matter undergoes, every exotic state it enters, every bizarre configuration it adopts is part of a desperate, furious fight against the force that is trying to erase it from the universe. That force is gravity. And tonight, we need to understand exactly how matter fights back, what weapons it has at its disposal, and why even the most powerful defenses the universe can muster eventually have limits. Because this battle, this contest between gravity and pressure at the heart of a near-threshold neutron star, is not just an astrophysical curiosity. It is a window into the deepest laws of physics. The outcome of this battle determines whether matter survives or whether it vanishes behind an event horizon forever. And the rules that govern it connect quantum mechanics, nuclear physics, and general relativity in ways that we are still struggling to fully understand. Let us start with the most fundamental source of resistance, the force that keeps neutron stars alive in the first place. It comes from quantum mechanics, and it is called degeneracy pressure. Degeneracy pressure is one of the strangest consequences of quantum mechanics. It has no analogue in classical physics. It is not like the pressure you feel when you inflate a balloon, which comes from gas molecules bouncing off the walls. It is not like the pressure inside a compressed spring, which comes from electromagnetic forces between atoms being pushed closer than their equilibrium distance. Degeneracy pressure arises from a purely quantum mechanical principle that governs how certain types of particles behave when they are packed closely together. The principle is called the Pauli exclusion principle, and it applies to all particles classified as fermions. Fermions include electrons, protons, and neutrons, the three particles that make up ordinary matter. The Pauli exclusion principle states something deceptively simple. No two identical fermions can occupy the same quantum state at the same time. Two electrons in an atom cannot have exactly the same set of quantum numbers. Two neutrons in a neutron star cannot be in precisely the same quantum state simultaneously. Each fermion must have something different about it, some quantum property that distinguishes it from every other identical fermion in the system. Under normal conditions, this principle has subtle effects, shaping the shell structure of atoms and the periodic table. But under extreme compression, it becomes a source of immense pressure. Here is why. When you compress a collection of fermions into a smaller volume, you are forcing them to occupy a smaller region of space. But quantum mechanics links spatial confinement to momentum. The Heisenberg uncertainty principle tells us that the more precisely you know a particle's position, the less precisely you can know its momentum, and vice versa. Confining fermions to a smaller space means their momenta must spread over a wider range. Some of the particles are forced into very high momentum states because all the lower momentum states are already occupied. These high momentum particles exert pressure outward, resisting further compression. The more you squeeze, the higher the momenta become, and the harder the particles push back. This is degeneracy pressure. It does not depend on temperature. It does not require the particles to be hot. It is purely a consequence of quantum statistics. Even at absolute zero, with no thermal energy whatsoever, degeneracy pressure would still exist because the Pauli exclusion principle still applies. You cannot compress identical fermions into the same quantum state, no matter how cold they are. In white dwarf stars, it is electron degeneracy pressure that holds the star up against gravity. The electrons in a white dwarf are packed so tightly that the Pauli exclusion principle generates enough pressure to resist the gravitational pull of a stellar mass, compressed into a sphere the size of Earth. This works remarkably well for white dwarfs up to approximately 1.4 solar masses. Above that limit, the Chandrasekhar limit, gravity overwhelms electron degeneracy pressure and the white dwarf collapses. In a neutron star, the electrons have already been absorbed into the protons, producing neutrons. Now it is the neutrons themselves that provide degeneracy pressure. Neutrons are fermions, just like electrons, so they obey the Pauli exclusion principle. And because neutrons are much more massive than electrons, about 1,836 times heavier, they can be compressed to much higher densities before their degeneracy pressure becomes significant. But once it does become significant, it is enormous. Neutron degeneracy pressure is what creates the initial resistance that halts the collapse of a massive star's core and produces a neutron star in the first place. But here is the critical insight for understanding near-threshold neutron stars. Neutron degeneracy pressure alone is not sufficient to explain the existence of neutron stars at the masses we observe. If neutron degeneracy pressure were the only force resisting gravity, the maximum mass a neutron star could sustain would be only about 0.7 solar masses. That is well below the masses of any neutron star we have actually observed. The lightest known neutron stars have masses around 1.2 solar masses, and many have masses near or above 2 solar masses. Something else must be providing additional pressure beyond what degeneracy alone can supply. That something else is the strong nuclear force. We touched on the strong force earlier, but now we need to examine it more carefully, because at near-threshold densities, the strong force is not merely an additional contributor to the pressure, it is the decisive factor. The behavior of the strong force at extreme densities determines whether a neutron star of a given mass can survive, or whether it collapses into a black hole. And the details of that behavior are among the most difficult and consequential problems in all of physics. Under ordinary conditions, the strong nuclear force acts between protons and neutrons, holding them together inside atomic nuclei. At the distances found inside a typical nucleus, the strong force is attractive. It pulls nucleons toward each other, binding them into the compact structures we call nuclei. Without this attractive force, nuclei could not exist. Protons, which all carry positive electric charge, would repel each other electromagnetically, and nuclei would fly apart. The strong force overcomes this electromagnetic repulsion, gluing nucleons together at nuclear distances. But the strong force is not purely attractive. At very short distances, shorter than the typical spacing between nucleons in an ordinary nucleus, the force becomes powerfully repulsive. This is sometimes called the repulsive core of the nuclear force. Think of it this way. the strong force acts like a peculiar spring connecting two nucleons. At moderate distances, the spring pulls them together. But if you push the nucleons too close, closer than the spring's natural resting length, it suddenly starts pushing them apart with tremendous force. There is a sweet spot where nucleons are bound together at a comfortable distance. Push them closer than that, and the force fights back violently. In ordinary nuclear matter, this repulsive core is essentially irrelevant. Nucleons sit at their equilibrium spacing, held there by the attractive part of the force. The repulsive core is dormant. It exists in principle, but conditions never activate it. Inside a massive neutron star, conditions are entirely different. The gravitational pressure is so immense that neutrons are being forced far closer together than they would ever be in an ordinary nucleus. The equilibrium spacing has been violated. The repulsive core of the nuclear force has been activated, and it is pushing back against gravity with tremendous power. This repulsive force is what allows neutron stars to exist at masses above the roughly 0.7 solar mass limit that degeneracy pressure alone could support. Without it, no neutron star above that mass could survive. The strong force repulsion at short range provides the additional pressure that extends the Tolman-Oppenheimer-Volkoff limit up to approximately 2 to 2.5 solar masses. And here is where the physics becomes genuinely uncertain. We understand the strong force reasonably well at the densities found inside ordinary atomic nuclei. Decades of experiments using particle accelerators and nuclear reactors have given us a detailed, quantitative understanding of how protons and neutrons interact at nuclear densities. We know the strength of the attractive force. We know where the repulsive core kicks in. We have mathematical models that reproduce the measured properties of nuclei with impressive accuracy. But the conditions in the core of a near-threshold neutron star are not the conditions of an ordinary nucleus. The density is several times higher than nuclear density. The neutrons are closer together than they have ever been in any nucleus we have studied. And at these extreme spacings, our knowledge of the strong force becomes increasingly uncertain. We are extrapolating beyond the regime where we have direct experimental data. We are relying on theoretical models that have been tested at lower densities and extending them into territory where they may or may not be accurate. Different models of the strong force at extreme densities give different predictions for how much pressure the matter can produce. And these differences have profound consequences, because the pressure at these densities determines the maximum mass a neutron star can sustain. It determines the Tolman-Oppenheimer-Volkoff limit. It determines the boundary between neutron stars and black holes. This is the equation of state, and it is the single most important concept for understanding near-threshold neutron stars. The equation of state is simply the relationship between pressure and density for a given type of matter. It tells you how much pressure the matter produces at any given density. For ordinary materials, the equation of state is well understood. We know exactly how much pressure water exerts at a given density and temperature. We know the equation of state for steel, for air, for helium, for any substance we can study in a laboratory. But for the matter inside a neutron star at densities several times above nuclear density, the equation of state is unknown. We cannot create these conditions in a laboratory. We cannot directly measure the pressure at these densities. We must infer the equation of state indirectly, from observations of neutron stars and from theoretical models of the strong force. A stiff equation of state means the matter pushes back hard, supporting larger maximum masses and producing larger neutron stars. A soft equation of state means less pressure, lower maximum masses, and more compact stars. The difference is not academic. It determines whether a given stellar remnant survives as a neutron star or collapses into a black hole. It determines how many black holes the universe contains, how many neutron stars there are, and what happens when two neutron stars collide. The equation of state is the rulebook governing the most extreme states of matter, and we are still trying to read it. Over the past decade, enormous progress has been made in constraining the equation of state through observations. The most dramatic breakthrough came on August 17, 2017, when the LIGO and Virgo gravitational wave observatories detected the signal designated GW170817. This was the first confirmed detection of gravitational waves from two neutron stars spiraling toward each other and merging. The event was also observed across the electromagnetic spectrum, from gamma rays to radio waves, making it the most thoroughly studied astrophysical event in history. The gravitational wave signal from this merger contained precious information about the equation of state. As the two neutron stars orbited each other in the final minutes and seconds before collision, the gravitational field of each star distorted the shape of the other. This tidal distortion depends on how easily the star deforms, which depends on its internal structure, which depends on the equation of state. A neutron star with a stiff equation of state is larger and more easily deformed by a companion's tidal field. A neutron star with a soft equation of state is more compact and resists deformation more effectively. The amount of tidal deformation affects the gravitational wave signal in a measurable way. It changes the precise pattern of the waves emitted during the last few orbits before merger. By analyzing the detected signal and comparing it to theoretical predictions from different equations of state, physicists were able to constrain the tidal deformability of the merging neutron stars. The result ruled out the stiffest equations of state. The neutron stars could not have been as large and fluffy as the stiffest models predicted. The equation of state must be moderate, producing enough pressure to support two solar mass neutron stars, but not so much that it makes them excessively large and easily deformed. This single observation eliminated entire families of theoretical models. Years of theoretical work predicting various equations of state were suddenly confronted with hard data. Models that predicted neutron star radii above about 13 kilometers were disfavored. Models that predicted radii below about 10.5 kilometers were also in tension, because the neutron stars needed to be large enough to support the masses inferred from the signal. The equation of state was being squeezed from both sides, narrowed to a band of possibilities that was much smaller than what theorists had been working with before. But this was just the beginning. Pulsar timing observations have provided some of the most precise neutron star mass measurements ever made. A pulsar is a rapidly spinning neutron star that emits beams of radio waves from its magnetic poles. As the star rotates, these beams sweep across space like the beam of a lighthouse. If one of these beams happens to point toward Earth during each rotation, we detect regular pulses of radio emission, one pulse per rotation. The timing of these pulses can be measured with extraordinary precision, to accuracies of billionths of a second. When a pulsar is in a binary system, orbiting another star, the pulse timing reveals the orbital dynamics. From the orbit, physicists can extract the masses of both stars using general relativity. Several millisecond pulsars, which are old neutron stars spun up to rotation periods of just a few milliseconds by accreting matter from a companion, have been weighed this way with remarkable accuracy. The pulsar designated PSRJ0740 plus 6620 is one of the most massive neutron stars ever measured, with a mass of approximately 2.08 solar masses. This measurement used a relativistic effect called the Shapiro delay, a tiny slowing of the pulsar's radio signal as it passes through the curved spacetime near its companion star. The precision of this measurement is extraordinary, with uncertainties of only a few hundredths of a solar mass. This single object tells us that the equation of state must be stiff enough to support at least 2.08 solar masses. Any model predicting a maximum mass below this value is immediately ruled out. The Neutron Star Interior Composition Explorer aboard the International Space Station has added another critical piece. NICER measures X-ray emission from the surfaces of neutron stars as they rotate. Hotspots on the surface produce pulsations in the X-ray signal. By modelling these pulsations, accounting for the way general relativity bends light near the neutron star's surface, NICER can estimate both the mass and the radius of the star simultaneously. These mass-radius measurements directly constrain the equation of state, because each equation of state predicts a specific relationship between mass and radius. If NICER measures a neutron star's mass and radius, it can be plotted on a mass-radius diagram, and any equation of state curve that does not pass through that point is ruled out. NICER has measured several neutron stars, and the results consistently point toward radii of roughly 12 to 13 kilometers for neutron stars of about 1.4 solar masses. This is consistent with a moderately stiff equation of state. Not too stiff, not too soft. Enough pressure to support heavy neutron stars at reasonable sizes, but not so much pressure that the stars are enormously bloated. These observations, gravitational waves from mergers, pulsar mass measurements, NICER radius determinations, are converging on a consistent picture. The equation of state of ultra-dense matter is being mapped out, not through laboratory experiments, but through astronomical observations of the most extreme objects in the universe. We are using the universe itself as a laboratory, with neutron stars as the experimental apparatus and gravitational waves and electromagnetic radiation as the readout. But there is still significant uncertainty in the deep core. The observations constrain the equation of state most strongly at densities around nuclear density and up to about twice nuclear density. At higher densities, the kind found in the innermost cores of the most massive neutron stars near the Tolman-Oppenheimer-Volkoff limit, the constraints become weaker. There is room for surprises. A phase transition to quark matter could occur at these higher densities, changing the equation of state in ways that might not be visible in current observations. Hyperons could appear and soften the equation of state in a narrow density range that current measurements are not sensitive to. The inner core could contain states of matter that behave very differently from what we observe at lower densities, and we might not detect this with our current tools. This is why the near-threshold regime is so scientifically important. It is the regime where the equation of state matters most, where the difference between a slightly stiffer and a slightly softer behavior of matter determines life or death for the star, where a phase transition from neutron matter to quark matter could shift the maximum mass by 1/10 of a solar mass, and that 1/10 of a solar mass determines whether a particular remnant becomes a neutron star or a black hole. Now let us think about what is actually happening inside a near-threshold neutron star in terms of the balance between gravity and pressure. Because the balance at this extreme mass is qualitatively different from the balance in a lower mass neutron star. In a lower mass neutron star, say 1.4 solar masses, there is a comfortable margin between gravity's pull and the internal pressure's resistance. The star is dense and extreme, but it is well within its structural limits. You could add a significant amount of mass before approaching the Tolman-Oppenheimer-Volkoff limit. The star has reserve capacity. It could absorb perturbations, mergers of small amounts of additional material, and remain stable. There is room between where it is and where it would need to be for gravity to win. In a near-threshold neutron star, that margin has shrunk to almost nothing. The star is operating at the very edge of what its internal pressure can sustain. Gravity is pulling inward with a force that is only infinitesimally less than the maximum outward pressure the matter can produce. The star is balanced on a razor's edge. The slightest change could tip it over. And here is what makes this so precarious. As the star approaches its maximum mass, a dangerous feedback mechanism begins to operate. General relativity, Einstein's theory of gravity, tells us that pressure itself contributes to the gravitational field. In Newtonian gravity, the old pre-Einstein theory, only mass creates gravitational attraction. The more massive an object is, the stronger its gravity. Pressure has nothing to do with it. But in general relativity, which is the correct theory of gravity, energy and pressure both contribute to the curvature of spacetime. Both generate gravity. This means that the very pressure holding the star up also adds to the gravitational force trying to crush it. At moderate densities, this is a minor correction. At near-threshold densities, it creates a dangerous feedback loop. More pressure means more gravity, requiring even more pressure, generating even more gravity. In Newtonian gravity, where pressure does not contribute to gravity, there would be no upper mass limit. But general relativity changes the equation. There is a point beyond which adding more pressure makes things worse. The additional gravity exceeds the additional support. At that point, no equation of state can prevent collapse. This is profound. It means the Tolman-Oppenheimer-Volkoff limit is not just a consequence of nuclear physics. It is a consequence of general relativity itself. The structure of spacetime places a fundamental limit on how massive a neutron star can be, independent of the details of what the matter is made of. The details of the equation of state determine the precise value of the limit, whether it is 2 solar masses, or 2.5 solar masses, or something in between. But the existence of a limit is guaranteed by general relativity. No form of matter, no equation of state, no exotic physics can push the maximum mass above roughly 3 solar masses, because at that point, general relativity's pressure-gravity feedback makes collapse inevitable regardless of the internal physics. There is one more source of resistance we should discuss, one that operates specifically when neutron stars are pushed to the absolute edge. In certain conditions, the matter may undergo phase transitions that temporarily provide additional pressure or create density plateaus that resist further compression. Imagine a neutron star slowly gaining mass from a companion star. As the mass increases, the central density rises. At some critical density, the matter might undergo a transition from one phase to another, perhaps from pure neutron matter to a mixture of neutrons and hyperons, or from nuclear matter to deconfined quark matter. If this transition releases energy or creates a stiffer state of matter at the new phase, it could provide a temporary boost to the pressure, delaying collapse. Conversely, if the transition softens the equation of state, it could trigger a premature collapse, causing the star to implode into a black hole at a mass lower than what neutron matter alone could support. Phase transitions inside neutron stars are one of the most active areas of research in nuclear astrophysics precisely because their effects on the maximum mass are so consequential. A strong first-order phase transition, one that involves a sudden jump in density at a specific pressure, could create an entire branch of compact stars with different properties from ordinary neutron stars. These hypothetical objects are sometimes called hybrid stars, neutron stars with quark matter cores, or even strange stars, objects made entirely of deconfined quark matter containing strange quarks in addition to up and down quarks.
Whether these objects exist depends on details of the strong force at extreme densities that remain uncertain. Future gravitational wave observations will be crucial for resolving these questions. When two neutron stars merge, the violence of the collision probes the equation of state at densities well above what exists in any stable neutron star. The immediate aftermath of a merger, the first few milliseconds, involves densities and temperatures that briefly exceed those found even in the core of a near-threshold neutron star. The gravitational wave signal from this post-merger phase contains information about the equation of state at the highest densities, information that could reveal phase transitions and exotic states of matter that are invisible in observations of individual static neutron stars. Current gravitational wave detectors are not quite sensitive enough to extract detailed information from the post-merger signal. The merger happens at high frequencies, at the edge of, or beyond, the range where LIGO and Virgo are most sensitive. But next-generation detectors including upgrades planned for the late 2020s and entirely new facilities proposed for the 2030s, will have dramatically improved sensitivity at these higher frequencies. They will be able to observe the post-merger signal in detail, potentially revealing the equation of state at the most extreme densities, and answering whether phase transitions occur during the catastrophic final moments of a neutron-star collision. There is also the tantalizing possibility that we might observe the collapse of a near-threshold neutron star in real time. If a massive neutron star in a binary system is slowly gaining mass from its companion, it will eventually cross the Tolman-Oppenheimer-Volkoff limit and collapse. The collapse would happen in milliseconds, far too fast for any human to witness directly, but it would produce a distinctive gravitational wave signal, a sharp burst as the star implodes. If a gravitational wave detector happens to be listening at the right moment, pointed in the right direction, it could catch the signal of a neutron star crossing the threshold and becoming a black hole. This would be an extraordinary observation, a direct measurement of the maximum neutron star mass, which would pin down the equation of state at the highest densities better than any other observation possibly could. So let us step back and summarize what we have learned about the resistance. A near-threshold neutron star resists gravitational collapse through multiple mechanisms working together. Neutron degeneracy pressure provides a baseline resistance, a quantum mechanical flaw that prevents neutrons from being squeezed into the same quantum state. The repulsive core of the strong nuclear force provides additional pressure at extremely short distances, pushing neutrons apart when gravity forces them closer than their natural equilibrium spacing. Possible exotic phases of matter, whether quark matter, meson condensates, or other unknown states, may contribute additional or reduced pressure, depending on their specific properties. And general relativity's requirement that pressure itself generates gravity creates a feedback loop that ultimately limits how much pressure can help, no matter how stiff the equation of state becomes. Together, these mechanisms establish a maximum mass for neutron stars. Above this mass, no known force or phenomenon can prevent collapse. The matter has exhausted every defense available to it. Degeneracy pressure is at its maximum. The strong force repulsion is fully engaged. Every exotic phase transition that might provide additional stiffness has either already occurred or is insufficient to make a difference. Gravity, amplified by the relativistic contribution of the pressure itself, overwhelms everything, and the star falls. But that fall, that crossing of the threshold from a near-threshold compact object to a black hole, is not a vague or gradual process. It is sharp. It is absolute. It involves the formation of something that is, qualitatively, fundamentally different from anything that existed before. An event horizon. A boundary in space-time from which nothing, not light, not information, not any signal of any kind, can ever escape. The difference between a near-threshold neutron star and a black hole is not merely a difference of degree. It is not like the difference between a warm room and a hot room, where the same thing exists but at different intensities. It is a difference of kind. On one side of the threshold, matter exists. It has structure, it has pressure, it has temperature, it has composition. On the other side, all of that is gone, replaced by a region of pure space-time geometry defined by just three numbers: mass, spin, and electric charge. Nothing else survives the crossing. Understanding what holds a near-threshold neutron star together and why that resistance eventually fails is therefore one of the deepest questions we can ask about the physical universe. It connects the quantum world of fermions and exclusion principles to the relativistic world of curved spacetime and event horizons.
It connects the smallest scales of nuclear physics to the largest scales of stellar evolution and gravitational wave astronomy. It connects the most fundamental theories we possess to the most extreme environments the universe creates. And at the heart of it all is a simple, terrifying question. What happens when the last defense fails? What does it look like when a near-threshold neutron star loses its battle with gravity, crosses the line, and becomes something from which nothing can return? That question, the question of what separates a star that almost becomes a black hole from one that actually does, is where our journey reaches its final destination. We have travelled through every layer of a star sitting on the edge of oblivion. We have watched matter transform from atomic nuclei into nuclear pasta, from superfluid neutrons into possibly deconfined quarks. We have examined every defense the matter can muster against gravitational collapse, and we have seen that those defenses, however powerful, have limits. Now it is time to confront the final question directly. What separates a near-threshold compact object from an actual black hole? What is the line between a star that almost becomes a black hole and one that actually does? And what happens in the moment that line is crossed? Because the difference between these two objects is not subtle. It is not a matter of degree. It is one of the sharpest, most absolute distinctions in all of physics. On one side, matter exists. On the other side, matter, as we understand it, ceases to have any meaning. And the boundary between them is defined by something that has no parallel anywhere else in nature: the event horizon. An event horizon is not a physical surface. It is not a wall or a membrane or a barrier made of some substance. If you were falling into a black hole, you would not feel yourself hitting anything when you crossed the event horizon. You would not see a glowing boundary or hear a warning sound. In fact, from your own perspective, nothing special would happen at the moment of crossing. You would simply continue falling, seeing the stars above you and the darkness below, unaware that you had just crossed a point of no return. But you would have, because the event horizon is a boundary in space-time itself. It is the surface beyond which the curvature of space-time has become so extreme that all paths, even paths taken by light travelling at 300,000 kilometers per second, curve back inward. Every direction becomes inward. There is no trajectory, no speed, no maneuver that can carry you back across the horizon once you have crossed it. Not because something is blocking your way, but because the geometry of space-time itself has closed around you. The exit does not exist. This is what makes a black hole fundamentally different from a near-threshold neutron star. A neutron star, no matter how dense, no matter how extreme, has a surface. It has an exterior. Light emitted from its surface can travel outward into space and be seen by distant observers. Information about what is happening on and inside the neutron star can, in principle, escape. The star interacts with the rest of the universe. It emits X-rays. It produces gravitational waves during mergers. It emits neutrinos from its hot interior. It has a magnetic field that extends into space and accelerates particles to enormous energies. It is part of the observable universe. It exists within the causal fabric of space-time that connects everything else. A black hole does not have these properties. Once an event horizon forms, the interior is causally disconnected from the exterior. Nothing that happens inside can influence anything outside. No signal can escape. No light can emerge. No information about the internal structure, composition, temperature, or state of the matter can ever reach an outside observer. The matter that once had structure, that once resisted gravity, that once existed as something with properties and characteristics, is hidden behind a one-way boundary in space-time. For all practical purposes, from the perspective of the outside universe, it is gone. The event horizon of a non-rotating black hole is a perfect sphere whose radius depends only on the mass. For a 2 solar mass black hole, roughly the mass at which a near-threshold neutron star would collapse, the event horizon radius would be about 6 kilometers, compared to the neutron star's 10 to 12. But the consequences of crossing that threshold are infinite, because once the event horizon forms, the collapse does not stop. There is no longer any force that can halt the collapse. The matter continues falling inward, past where the event horizon now sits, continuing to compress without limit. According to general relativity, the matter falls all the way to a singularity, a point of infinite density at the center of the black hole. At the singularity, the equations of general relativity produce infinite values for density, curvature, and gravitational force. These infinities are generally understood as a signal that general relativity is breaking down. That at these extreme conditions, a quantum theory of gravity is needed to describe what actually happens. We do not have such a theory. So, we genuinely do not know what happens at the center of a black hole. The singularity may not be a true physical entity. It may be replaced by something finite and quantum mechanical, a region of Planck scale density where quantum gravity effects prevent the collapse from reaching truly infinite values. But we cannot calculate what that something is with any confidence, because we lack the theoretical tools. What we do know is that the event horizon marks an absolute boundary, and the formation of that boundary is what distinguishes a black hole from everything else. A near-threshold neutron star can be observed, studied, measured, and understood. A black hole, once formed, reveals almost nothing about the matter that created it. This is encapsulated in a remarkable result called the no-hair theorem. It states that a black hole in equilibrium is completely described by just 3 numbers: its mass, its spin, and its electric charge. Nothing else. Not what it was made of, not how many neutrons or quarks or hyperons were in the star before it collapsed. Not whether the matter contained deconfined quark matter, nuclear pasta, or superfluid neutrons. All of that information is lost behind the event horizon. The black hole remembers nothing about its past, except how much mass it has, how fast it is spinning, and how much charge it carries. 2 black holes with the same mass, spin, and charge are completely identical, regardless of whether one formed from a collapsing neutron star and the other formed from an entirely different process. The matter's identity has been erased. The threshold between a near-threshold neutron star and a black hole is therefore not just a threshold of density or pressure, it is a threshold of information. On one side, a rich, complex object with structure and quantum mechanical behavior. On the other hand, a featureless geometric object is described by 3 numbers. The crossing represents a catastrophic loss of physical information. Now let us consider how that threshold is actually crossed. How does a near-threshold neutron star become a black hole? There are several scenarios, and each one reveals something important about the physics of the boundary. The most straightforward scenario involves accretion. A neutron star in a binary system orbiting a companion star can gradually accumulate mass. Material from the companion, usually hydrogen and helium gas, streams across the space between the 2 stars and falls onto the neutron star's surface. This process can continue for millions or billions of years, slowly increasing the neutron star's mass gram by gram, kilogram by kilogram, year by year. As the mass increases, the central density of the neutron star rises. The core is compressed further. The matter is pushed into ever more extreme states. The balance between gravity and pressure tightens. The margin of safety shrinks. And at some point, the neutron star's mass crosses the Tolman-Oppenheimer-Volkoff limit. The moment it does,
the internal pressure can no longer support the star against gravity. The collapse happens almost instantaneously. In a matter of milliseconds, the entire neutron star, an object that may have existed stably for billions of years, implodes. An event horizon forms. The matter disappears behind it. A black hole is born. The speed of this collapse is difficult to overstate. From the moment the critical mass is exceeded to the formation of the event horizon, the elapsed time is measured in milliseconds, thousandths of a second. A blink of a human eye takes about 300 milliseconds. The collapse of a neutron star into a black hole takes a small fraction of that. An object that endured for eons is destroyed in an instant. The second scenario is far more violent. It involves the merger of two neutron stars. When two neutron stars in a binary system spiral toward each other, losing energy through gravitational wave emission over millions of years, they eventually collide. The collision is among the most energetic events in the universe. In the final milliseconds before impact, the two stars are orbiting each other at a significant fraction of the speed of light, completing hundreds of orbits per second. The gravitational wave emission is intense, carrying away energy at a prodigious rate. And then the two stars make contact. The merger is catastrophic. The two neutron stars smash together at speeds of tens of thousands of kilometers per second. In the final millisecond before contact, the two stars are orbiting each other hundreds of times per second. The gravitational waves pouring off the system carry away energy equivalent to a significant fraction of a solar mass, converted entirely into ripples in spacetime. The stars are being stretched and squeezed by each other's tidal fields, their shapes distorting from spheres into elongated teardrops, reaching toward each other across the narrowing gap. Then contact. The two surfaces of nuclear density matter collide. The impact sends shockwaves ripping through both stars. Material at the collision interface is heated to temperatures exceeding anything found inside even the most massive, stable neutron star. Jets of matter are flung outward at nearly the speed of light. The impact generates temperatures of hundreds of billions of degrees. Matter is flung outward in all directions. Heavy elements, gold, platinum, and uranium, are forged in the nuclear furnace at the collision and ejected into space in a brilliant flash called a kilonova. This is where most of the gold, platinum, and uranium in the universe actually come from. For decades, physicists debated whether these heaviest elements were forged primarily in supernovae or in neutron star mergers. The observation of the kilonova following GW 170817 provided strong evidence that mergers are a dominant source. The gold in a wedding ring, the platinum in a circuit board, the uranium in a reactor, much of it was likely created in the violent collision of two neutron stars billions of years ago, long before our solar system formed. A single neutron star merger can produce several Earth masses worth of gold and platinum in a fraction of a second. The total mass of heavy elements ejected in one collision can exceed several times the mass of Jupiter. All of it forged in an environment so extreme that it exists for only milliseconds before being flung across interstellar space, eventually to be incorporated into new stars, new planets, and new worlds. Gravitational waves pour out with enormous intensity. Neutrinos flood the surrounding space, and at the center of this maelstrom, something remarkable happens. The combined mass of the two neutron stars almost always exceeds the Tolman-Oppenheimer-Volkoff limit. If the combined mass is high enough, the remnant collapses into a black hole almost immediately, within a few milliseconds of the merger. But if the combined mass is only slightly above the limit, something extraordinary occurs. The remnant does not collapse right away. Instead, it forms a temporary object that exists for a brief, violent moment before succumbing to gravity. These temporary objects are called hypermassive neutron stars and supramassive neutron stars, and they represent some of the most extreme conditions that matter can experience anywhere in the universe,
even more extreme than the conditions inside a stable, near-threshold neutron star. A hypermassive neutron star is supported by differential rotation, thermal pressure, and amplified magnetic fields, effects that only exist because the remnant is spinning rapidly and far from equilibrium. But these supports are temporary. Differential rotation is damped. Thermal energy radiates away. Within milliseconds to hundreds of milliseconds, it collapses. A supramassive neutron star, supported by uniform rotation, can survive longer, potentially for seconds or minutes. But as it loses rotational energy and spins down, it too collapses into a black hole. These temporary states are extraordinarily important scientifically because they probe the equation of state at conditions beyond what any stable neutron star can reach. The densities and temperatures inside a hypermassive neutron star in the first few milliseconds after a merger exceed anything found in a static star. The matter is hotter, denser, more turbulent, and more violently churning than anything that exists anywhere else in the universe. And the gravitational wave signal from this brief post-merger phase contains information about the equation of state at these unprecedented conditions. The merger event GW170817 gave us our first glimpse of this process. The gravitational wave signal clearly showed the inspiral phase, the two neutron stars orbiting each other and spiraling closer. It showed the moment of merger. But the post-merger signal, the part that would reveal whether a hypermassive neutron star formed and how long it lasted before collapsing, was at frequencies too high for the detectors to measure clearly. We know the merger produced a remnant. We know that the remnant eventually formed a black hole. But we do not know exactly how long the intermediate state lasted, or what happened during those critical milliseconds.
Future gravitational wave detectors will change this. The next generation of observatories, including proposed facilities like Cosmic Explorer and the Einstein telescope, will have dramatically improved sensitivity at the higher frequencies where the post-merger signal lives. They will be able to observe the formation and collapse of hypermassive neutron stars in detail, measuring how long the temporary remnant survives, how it oscillates, and how the gravitational wave signal changes at the moment of black hole formation. These observations will provide direct measurements of the equation of state at the most extreme densities, at conditions that push beyond the Tolman-Oppenheimer-Volkoff limit into territory that no stable object can occupy. The scientific stakes of understanding the near-threshold regime extend far beyond astrophysics. This regime is where several of the most fundamental areas of physics converge and interact. It tests general relativity in the strong field regime, where gravitational fields are so intense that space-time curvature is not a small correction, but the dominant feature of the environment. It tests nuclear physics at densities far beyond anything achievable in terrestrial laboratories. It tests quantum mechanics under conditions where quantum degeneracy pressure is pushed to its limits, and where quantum phase transitions may determine the fate of an entire star. And it connects all of these through the equation of state, a single function that encodes the behavior of matter at the most extreme conditions the universe allows. Understanding the equation of state is not merely about knowing the properties of neutron stars. It is about understanding the fundamental nature of the strong nuclear force. The strong force is the least well understood of the four fundamental forces of nature at extreme densities. We understand electromagnetism exquisitely. We understand the weak nuclear force well enough to make precision predictions. Gravity, while mysterious at the quantum level, is beautifully described by general relativity at macroscopic scales. But the strong force at supranuclear densities, the regime inside massive neutron stars, remains deeply uncertain. The calculations required by quantum chromodynamics at these densities are among the most computationally demanding problems in all of science. Supercomputers running for months
can only approximate the behavior of strong force matter at densities somewhat above nuclear density. At the densities found in the cores of near-threshold neutron stars, even our best computational methods struggle. Neutron stars are therefore natural laboratories for the strong force. They are the only places in the universe where strong force matter at supranuclear densities exists stably and can be observed, however indirectly. Every mass measurement, every radius determination, every gravitational wave detection from a neutron star merger is, at its core, a measurement of the strong nuclear force under conditions that we cannot reproduce on Earth. The astronomical observations are not just telling us about neutron stars, they are telling us about quarks and gluons and the fundamental forces that hold matter together at the deepest level. There is also a profound connection to cosmology. The early universe, in the first microseconds after the Big Bang, was filled with quark-gluon plasma, the same deconfined state of matter that might exist inside near-threshold neutron stars. As the universe cooled, this plasma underwent a phase transition, condensing into the protons and neutrons that eventually formed atomic nuclei. Understanding the equation of state at extreme densities helps us understand this primordial phase transition and the conditions in the earliest moments of the universe's existence. The physics of neutron star cores and the physics of the Big Bang are connected through the same fundamental question. How does matter behave when it is pushed to its most extreme possible state? Now, let us step back and consider what all of this means. What is the deeper significance of a star that almost becomes a black hole? A near-threshold neutron star is the last outpost of the material world. It is the most extreme version of physical substance that the universe permits. Every atom has been dismantled. Every nucleus has been dissolved. Even the neutrons themselves may have lost their individual identities. What remains is a quantum fluid of extraordinary density, pushed to the absolute limit of what can resist gravitational collapse. And just beyond that limit, just a fraction of a solar mass beyond, lies the event horizon. The transition from matter to geometry, from substance to void, from something to, in a certain profound sense, nothing. This boundary is unlike any other boundary in physics. Most transitions between physical states are gradual. Water becomes ice through a smooth process of molecular rearrangement. Gas becomes plasma as atoms are ionized by increasing temperature. These transitions can be reversed. Ice melts back into water. Plasma recombines back into gas. The transition is between two different arrangements of the same underlying stuff. The transition from a near-threshold neutron star to a black hole is not like this. It is irreversible. Once the event horizon forms, the matter cannot re-emerge. It cannot transition back to a neutron star. The information about its structure and composition is lost. The transition is not between two states of matter. It is between matter existing and matter ceasing to be accessible to the rest of the universe. It is, in the most literal sense, a boundary between being and non-being, at least from the perspective of any observer outside the black hole. And yet, the matter does not vanish from the universe entirely. The mass remains. The gravity remains. A black hole with two solar masses has the same gravitational pull on distant objects as a neutron star with two solar masses. If our Sun were magically replaced by a black hole of the same mass, the planets would continue orbiting exactly as before. They would notice no difference in the gravitational field. The black hole's gravity reaches out across space just as the Sun's gravity does. What is lost is not the mass or the gravity, but the internal structure, the richness, the complexity, the story of what the matter was and how it got there. This connects to one of the deepest unsolved problems in theoretical physics, the black hole information paradox. Quantum mechanics insists that information is never truly destroyed, yet a black hole appears to violate this. When matter falls behind an event horizon, information about it seems lost. When the black hole eventually evaporates through Hawking radiation, the radiation appears to carry no information about what fell in. Either quantum mechanics is wrong, general relativity is wrong, or something else entirely is happening. This paradox has driven some of the most creative theoretical work in physics over the past 50 years, and all of it traces back to the threshold we have explored tonight. The near-threshold regime is where these questions become concrete rather than abstract. When a neutron star sits just below the Tolman-Oppenheimer-Volkoff limit, every quark, every gluon, every quantum state in its interior is, in principle, observable. We could measure the star's mass, its radius, its rotation rate, and its magnetic field. We could detect gravitational waves from its oscillations. We could observe X-rays from its surface. The star is part of our universe. It participates in the exchange of information that connects everything in the cosmos. But push that star just barely over the limit. Add one final fraction of a solar mass, and an event horizon forms. Suddenly, all of that information is cut off.
The quarks, the gluons, the quantum states that were accessible a moment ago are now hidden behind a one-way boundary in space-time. The transition from fully accessible to permanently hidden happens in milliseconds. The most extreme transformation in all of physics, occurring in the blink of an eye. This is why the near-threshold regime matters so deeply. Not just as a topic in astrophysics, not just as a test of nuclear physics or general relativity, but as a window into the deepest questions about the nature of reality, about what matter is and what it can become, about the relationship between quantum mechanics and gravity, about the limits of physical existence itself. Every neutron star near the maximum mass is a monument to the resilience of matter. An object where the fundamental particles of nature are marshalling every quantum mechanical and nuclear force at their disposal to resist being crushed out of existence. And every black hole that forms from a collapsing neutron star is a testament to the ultimate supremacy of gravity. A reminder that space-time curvature, when it becomes extreme enough, overwhelms everything else. Every force, every pressure, every quantum mechanical trick the particles can deploy. When gravity wins, it wins completely and irreversibly. Somewhere in our galaxy right now, there are neutron stars sitting on that edge. Stars so massive that their cores contain matter in states no human has ever directly observed. States where the boundaries between neutrons may have dissolved, where quarks might roam free, where the strong force is pushed to behaviors we can only theorize about. These stars are balanced between survival and annihilation, held up by pressures so immense they are difficult even to calculate, pressed inward by gravity so powerful it warps the very fabric of space and time around them. Some of these stars will survive. They will cool slowly over trillions of years, spinning in the darkness, gradually radiating away their heat, enduring long after the last ordinary stars have burned out. They will be among the final luminous objects in a darkening universe, relics of an era when stars still shone. Others will not survive. They will gain just enough mass from a companion or collide with another neutron star, and, in a fraction of a second, everything that made them what they were will vanish behind an event horizon. The matter that fought so hard to resist gravity will be silenced. The quantum pressures that held the star together for billions of years will be overwhelmed in milliseconds. And a black hole will form where a star once stood, a region of pure geometric curvature, carrying the mass but none of the memory of what came before. The boundary between these two fates is razor thin, a fraction of a solar mass. A slight shift in the equation of state, a tiny change in the behavior of the strong force at extreme densities. That is all that separates a near-threshold neutron star from a black hole.
all that separates existence from the event horizon, all that separates the last stand of matter from the total victory of gravity. And understanding that boundary, mapping it, measuring it, comprehending the physics that governs it, is one of the greatest scientific challenges of our time. It requires gravitational wave observatories listening for the whisper of colliding neutron stars across billions of light years. It requires X-ray telescopes orbiting Earth, measuring the sizes and masses of the densest objects in the cosmos. It requires theoretical physicists pushing the limits of quantum chromodynamics and general relativity on the most powerful supercomputers ever built. It requires particle accelerators probing the strong force at ever higher energies, narrowing the uncertainties in how matter behaves under extreme compression. All of these efforts converge on a single question: where does matter end and the black hole begin?
That question is not just about neutron stars or black holes. It is about the fundamental architecture of reality, about the rules the universe follows when it creates the most extreme objects possible, about what the cosmos permits to exist and what it forbids, about the last thing matter can be before it stops being matter at all. Tonight we have gone inside a star that almost becomes a black hole. We have seen what matter endures at the edge of gravitational collapse. We have watched it transform from atoms into nuclear fluid, from neutrons into possibly free quarks, resisting at every stage with every force nature provides. And we have seen that there is a limit, a line beyond which resistance is futile, beyond which the geometry of space-time itself forecloses every escape, beyond which matter, no matter what form it takes, can no longer hold on. That line is real. It exists somewhere inside the most massive neutron stars in our galaxy, and on one side of it, the universe contains the most extraordinary objects that matter can become. Objects where physics is pushed to its absolute extreme, where quantum mechanics and gravity collide, where the strong force reveals its deepest secrets under pressures that dwarf anything else in the cosmos. On the other side of that line, there is silence, an event horizon, a boundary from which nothing returns. And the distance between these two realities, the distance between the last surviving state of matter and the birth of a black hole, may be measured in fractions of a kilometre, in thousandths of a solar mass, in milliseconds of time. That is how close these stars come. That is how thin the line is between existence and oblivion. And that is why what happens inside a star that almost becomes a black hole is one of the most profound stories the universe has to tell.